Eckford from York University in Toronto, and I'll be talking about diversity analysis of irregular fractional cooperation. Okay, so by now we should all be familiar with what exactly cooperation is. So here I am standing here with my cell phone, wanting to communicate with the base station, and along comes another cell phone that's willing to help me out, that's willing to act as a relay. I bounce my signal off that handset, and potentially I can achieve a better path to the base station, or vice versa. It can be reversed, which is one of the key ideas of cooperation. So in fact, I used the cell phone because I found some easy clip art, but this is in fact a proposal in 4G networks. In 4G, it's anticipated that to achieve extremely high data rates, it will be necessary to actually have handsets using each other as relays in cooperation. So that brings up an interesting question. Within this room right now, I'm willing to bet that there are at least a dozen cell phones. And if I had my mobile with me, I'm willing to bet that within its radio range, I could potentially be able to access many dozens or perhaps even hundreds of potential relays. So there's lots of people willing to help me out. So what's a good scheme that can be used in order to access those resources? So what we're going to propose today is something a little different. We're going to talk about fractional cooperation. So in fractional cooperation, we have many available relays, as I mentioned. There's lots of cell phones out there that are available, that have radio links to the base station that I want to talk to. But each relay only contributes a fraction of its resources to relay. And this is a very practical assumption. So imagine you have your cell phone. So even imagine a case in which selection is used, which is viewed as a energy efficient way of achieving diversity gains. So even if selection is used, suppose you're standing in a very favorable spot so that everyone wants to select you as a relay. So are you willing to basically sacrifice your cell phone for the common good? Probably not. So what we're going to talk about today is, yeah, you're probably willing to help people out in order to get some help yourself, but you're probably not willing to dedicate the entire resources of your mobile handset to cooperation. So in fact, what we're going to do is we're going to take this scenario we had over here where we've got lots of relays. We're going to use all of them, so that basically solves the problem of who to use very simply, but we're only going to use a small fraction of each available relay. So here's basically how it works. The source transmits a sequence. So each of these little blue squares, let's say they represent bits or symbols or whatever the source is transmitting. Along comes a relay. The relay selects, it doesn't really matter how, but a good way to think about it is uniformly at random, according to some probability, the relay selects some random fraction of what the source transmitted and relays that small random fraction to the base station. So for example, if the relay is already transmitting its own information, it has its own packet to send, and these extra symbols are just piggybacking on top of that packet. So just a very small incremental increase in the energy used by the relay. So we're going to call it as we're going to refer to this as a cooperation sequence. So imagine that rectangle of blue and red squares as a vector with zeros in the blue spots and ones in the red spots, and that's the cooperation sequence used by this particular relay. So in other words, it's got a 1 in places where it selects a bit. And once again, it need not be random. You could do blocks, you could do just about anything. Our analysis covers all of those scenarios. So then so here's what's going on from the source's perspective. It transmits these bits. The blue ones are not relayed, the red ones are relayed. Then along comes another relay with its own cooperation sequence. Some of these bits could be selected twice. We're doing this in a distributed manner, so we're willing to tolerate that kind of waste. But the second relay selects its own random fraction of the bits, relays them, and now the source has these bits relayed. And this can go on and on and on, up to the many hundreds of possible available relays that I was talking about. So how do we analyze systems of this nature. So here's an observation that should be fairly obvious to most people in this room, but let's go back over it. So let's suppose a system outage is caused when, let me give you an example system, not necessarily fractional cooperation. And I tell you that a system outage is caused when some set of K relays have links with sufficiently low SNR. In fact, let's say that at least K relays have sufficiently low SNR in order to cause a system outage. In this case, it should be obvious that diversity order is K plus 1. So why is that? It's because each relay, the probability that that relay has sufficiently low SNR is on the order of 1 over average SNR. And if I have K relays, all of which are independent, then the probability that all of those relays are in SNR is 1 over average SNR to the power K. We add 1 because we have a direct link. So the diversity order, if K relays are critical to this situation, is K plus 1. Okay, so let's say, let's address a situation we refer to as regular fractional cooperation, in which every relay relays basically the same fraction. So let's say each relay will relay 1/4 of the bits that it observes, or actually in this scenario, it's probably better to think of it as 1/3. So let's say each relay is selecting 1/3 of the source's bits and transmitting them to the destination. So in previous work, we've shown that in this regular cooperation scenario, regular fractional cooperation scenario, for one thing, it should seem obvious that all the relays are indistinguishable. It doesn't really matter what set you use, or what relays you use, or how their SNRs are allocated by the channel. They're all indistinguishable from each other, statistically indistinguishable from each other, because they're all selecting the same fraction. So in this scenario, we define a quantity called RC. RC is the number of relays that are needed if the direct link is out. In other words, the direct link has 0 SNR. RC is the minimum number of relays you need to communicate using the relays alone. So RC is 3. That basically means that any 3 relays, if they have sufficiently high SNR, will be able to keep the system from going into outage. So it could be these 3 relays that have sufficiently high SNR, or these 3 relays, or these 3 relays. So what's the diversity order of this system? Well, let's combine this with the observation I had. So the observation was if any K relays cause outage, if K relays cause outage, the diversity order is K plus 1. So what's the diversity order here? We have 8 relays. If any 3 have sufficiently high SNR, then we're good. So what that means is the system can tolerate up to 5 relay failures. So 6 or more relay failures are bad. So if I have 5 relays that are out here, 1, 2, 3, 4, 5, any additional relay failure will cause that link to break if the direct link has 0 SNR. So this means, coupled with my observation, that my critical number K is 6. 6 plus 1 is 7. So the diversity order of this system is 7. So what's the cute thing about fractional cooperation? So remember, each of these guys is only relaying 1/3, let's say, for example, in this scenario, 1/3 of the original source's transmission. So if I add another relay, I get, even with only 1/3 energy investment, I get a full additional order of diversity, because in that case, the system only needs, let's say I had 9 relays, the system only needs 3 to succeed. So now the critical number is 7. 7 plus 1 is 8. The diversity order becomes 8, and so on. If I have 10 relays, my diversity order is 9. And this is, again, only requires the additional extra fraction